Hello students, welcome to the third part of our first module, CFF, Compressible Fluid Flow. So in this session, we are going to learn about the concept called acoustic velocity or velocity of sound. Okay, we will derive an equation for acoustic velocity, and we will discuss about uh, various form of acoustic velocity in various type of fluids. Okay, and also I will teach you about the concept called Mach number. Okay, so we'll start with acoustic velocity. So students, we have learned the concept called compressible fluid and compressible fluid flow. So both idea are a little bit different, right? So I have told you that compressible fluid is those fluid that undergo change in density due to various reasons. Okay, but compressible fluid flow is the flowing fluid may be incompressible, but the flow is compressible. Flow is compressible means due to some temperature change or velocity change, the fluid undergoes during the flow there will be some change of density. So that's the idea behind compressible fluid flow. Okay. So if the density of the fluid changes appreciably throughout the flow field, then the flow can be treated as compressible flow. Okay. So students, in most practical fluid flow systems, variation in density in case of CFF, that means compressible fluid flow. What is the cause of variation density? Cause is nothing but due to change in what? Pressure. In most of the cases, variation density is caused due to change in pressure of the fluid from one point to another. Okay, from one point to another. So the rate at which density changes with the change in pressure is very important in our study in the field of compressible fluid flow. The study of rate of change, rate of change, rate of change of density with change in pressure, or the concept dou rho by dou p. This is very important. So this concept or the change of density with the change in pressure, that parameter is very important in the study of compressible fluid flow. Okay. So the rate of change of density with the pressure is this concept is closely associated with the velocity of propagation of small pressure disturbance. Okay. So what is the concept called, this is closely related to what? To the concept, the velocity of propagation, velocity of propagation of a pressure pulse in the fluid. So this concept, the change in density of the fluid with respect to change in pressure, that parameter is closely related to what? The velocity of propagation of a pressure pulse in the fluid. Pressure pulse is nothing but a small pressure disturbance. Pressure pulse is nothing but small pressure disturbance in the fluid field. in the fluid field. Okay, so the velocity of pressure pulse is the cause plays an important role in determining the rate at which density changes with the change in pressure. So students, this pressure pulse or the small pressure disturbance in the fluid field is nothing but the velocity of pressure pulse or the velocity of small pressure disturbance in the fluid field is nothing but velocity of sound. Velocity of sound in that fluid. Okay, in that particular fluid, the velocity of sound or what? Acoustic velocity. Very important. Acoustic velocity. So this has gotten the velocity of sound or acoustic velocity in that particular fluid. Okay, it may vary from fluid to fluid. In that fluid, this acoustic velocity in that fluid plays an important role in determining in analyzing the compressible flow or analyze or determine the rate at which density changes with the change in pressure, that is dou rho by dou p. Okay, so students, we will derive an equation for acoustic velocity. Okay, suppose I am having a tube, a piston, so here some gases. Okay, some gas, stationary gas means velocity equal to 0. The velocity of gas is 0 means the velocity of the gas or the gas that is present in the tube is 0 means that the gas is stationary. Okay, so let this tube be insulated. Okay, so students, initially the gas is 0. Let the pressure of the fluid in that particular tube be P, and temperature T and density rho. Okay, temperature T, density rho, and I will draw once again. This is the tube. Okay, so insulated. Initial velocity is 0, v equal to 0, p rho t. These are the initial pressure, density and temperature of that fluid. So this was the fluid here. And students, let us try to move this piston to a distance of some piston to move for a time delta t. Okay, so it has reached a distance. Okay, so movement for a particular time period delta t, movement for a particular time period delta t. So the piston has covered, say if the piston is moving with the velocity dv, so the piston has covered a distance x. Okay, so students, when pistons start to move, due to the sudden acceleration of the piston, it acts as a disturbance. It will create a disturbance, and I am assuming the gas present in that particular tube is having a viscosity of 0, and there is no any wall effects or something like that. The fluid is purely inviscid fluid. Inviscid means no viscosity. Viscosity is 0. So there is no shear force and all. So no dispersion. So no heat transfer. No heat transfer. Q equal to 0. Everything like. So what happens when the piston moves towards right? A pressure disturbance will form, right? So this pressure disturbance is nothing but sound wave or pressure wave. Sound wave is created. So this sound wave thus generated propagates ahead of the piston at a speed a. The sound wave velocity is a. So it will travel ahead of the piston, right? So sound travels ahead of the piston, movement of piston. So the sound wave is nothing but a wave front will reach somewhere here because it travels ahead. So the same delta t, so for the same time period, the sound wave has traveled a distance of what L. So L is greater than x. L is greater than x. So students, what is L? L equal to nothing but speed of sound wave into delta t. What is x? Distance traveled by piston. This is distance traveled by wave. This is distance traveled by piston. So this is nothing but v. Sorry, dv delta t. dv delta t. Students, we have got two distance. L is nothing but distance traveled by wavefront. X is the distance traveled by piston, right? So students, the piston has moved a distance of x, and the wave is shown by the color yellow, and the wave has moved a distance by L, right? So students, initially there was the before compression. So here, so this much amount of gas is compressed, right? This much amount of, I am considering this much amount only. So this is my system, a control system I am considering for the study. For just for the purpose of study, I am considering this much amount of gas. The gas enclosed between the wavefront and the piston as of now. So before compression, density was rho, pressure was P, right? But after compression, density rho plus d rho, and pressure has become P plus dP. Let a small change of density and pressure is taking place. Okay. So here now the density has become rho plus d rho, and pressure has become P plus dP. Okay. So students, I am considering a distance of L minus x only. After compression L minus x, before compression L, length L. Before compression I am considering before compression the mass was distributed along length L. After compression the mass is distributed along L minus x only. So students, we know the equation of continuity. We know the equation of continuity or mass conservation equation. So the mass before conservation, before compression should be equal to mass after compression, right? Right. So I am applying this equation. So what was before compression? Before compression, mass can be calculated based on density rho into if area of the cross section area of tube is A, and length, I am considering length L, right? So this was the rho AL. And after compression, I am considering the mass is compressed to a length of L minus x only, right? After compression, M should become density will increase rho plus d rho. Area same, but length has decreased to L minus x, right? L minus x. So by the equation of continuity, rho A L should be equal to rho plus d rho into A into L. Sorry, L minus x. L minus x. So what is L and what is x? L is nothing but rho A L equal to rho plus uh, actually L can be written as acoustic velocity into delta t, right? Rho plus d rho into area into what again a delta t minus dv delta t. Okay, dv delta t. Students, I can rearrange this like rho a uh, into a delta t equal to rho plus d rho into a into a minus dv into delta t, right? So I can cancel delta t a, right? So what's remaining? Rho a equal to rho plus d rho into a minus dv, right? So this will become rho a equal to rho a minus rho dv plus a d rho minus d rho dv. So this can be cancelled because product of two infinitesimally small element or differential element will approach zero. So d rho into dv will be very small value, so it can be ignored. So remaining this and this also get cancelled. So what is remaining? A d rho will be equal to rho dv, right? So students, this can be written as dv equal to a d rho by rho. So just keep this equation as equation number 1. The small velocity with the piston is approaching is equal to product of acoustic velocity into change in density by original density. So keep this equation. So we have dealt with the conservation of mass equation. Now we will move to conservation of momentum equation. Conservation of momentum equation. Conservation of momentum equation. So students, we have already learned that we should be thorough with the 4 different equations. First one, mass equation or continuity equation. Second one, conservation of momentum equation. That is Newton's second law of motion. Third is conservation of energy equation, or we have derived the SFFE and all. That is steady state equation, energy equation. Fourth one is thermodynamics, second law of thermodynamics, that is entropy's equation. So all 4 should be known. Now I am using the second conservation of momentum equation. So what actually this equation says? Sigma total F acting will be equal to sigma sigma m, or the moment mass into velocity over cv, right? Plus m dot v out minus m dot v in, right? Since I'm taking that particular control system or control volume of length L. I can write this equation, conservation momentum, in this way, right? Actually, conservation of momentum is the sum of body force will be equal to, sorry, the O by dot T. dou by dou t of mcv plus m dot v out minus m dot v in. Since I am considering the here I have considered a steady flow equation. There is no change in uh, momentum with respect to time. I can cancel this. Anything with anything which has the time derivative, its value will be equal to 0 in case of steady flow. So I am considering here a steady flow. So students, the equation has become delta F equal to m dot V out minus m dot V in. Okay. So students, since this equation is based on control volume, but I have taken here control system only, right? So I didn't take a control volume here. So this equation can be written as delta F equal to m dot V before compression. Instead of out and in, I can write it as after compression minus before compression. After compression minus m dot before V before compression. Okay. So what is V after compression? V velocity of fluid after compression is dV, right? Velocity of V before compression before the gas was stationary, so V0. So what is m dot? M dot is nothing but rho a, and I am considering a length L. So rho L was the mass before mass, or rho plus rho plus d rho a into L minus x. You can use either, both are same. So I will use this here. So m dot is nothing but divided by delta t should be used, or dt, because this is rate, not m dot. So I am using the sigma f equal to rho a L by dt L by dt into before compression velocity was after compression velocity was dv minus rho a L by dt 0. So it will become rho a L by dt, you keep it like this, into v minus 0, dv minus 0 means dv only. So students, what is this value? L by dt is nothing but sound, velocity of sound. So you can use here delta d, okay, delta d. So in time interval delta t, what is the distance traveled by wave length L? So the L by delta t will be acoustic velocity. So this can be written as sigma f equal to rho area into A into V. Okay. So what is sigma F? What are the forces acting in this case? There are only two types of forces. What are the before compression? Before compression, F before compression, pressure force, pressure P into area, right? F after compression, sorry, not before and after. I will show you. So I will draw this picture. So after compression, force F will is equal to some pressure has increased from P plus dP into A. So what is the that net force acting at the moment, since dP into A minus P into A. So this will be the net force acting. So this will be equal to dp into area. dp into area. So sigma f will be adp. adp, right? So ADP should be equal to rho A into small a into dB. So this will give you dB equal to dP by area cancel dP by rho A. Let this equation be 2. So comparing equation 1 is nothing but dV equal to A d rho by rho. Equation 2 using continuity equation dV you get dP by rho A. So since both equation 1 and 2 are having the left hand side same dV, you can write A d rho by rho will be equal to dP by rho A. So you will get A square equal to dP by dP by rho, sorry, dP by d rho, right? dP by d rho. So rho and rho cancel. Actually, how was that? A d rho by rho was equal to dP by a rho, right? So rho and rho cancel. A goes here. So a square will become d rho by, sorry, dP by t rho. Alright. So a will be equal to square root of dou, so dP by d rho. Since we have considered no change in, no heat transfer from the body, that is Q equal to 0. We have insulated the tube, and then there is no dissipation due to any, no dissipation due to viscosity, due to shear force and all. Since since the viscosity of fluid is 0, there won't be any shear force, there won't be any dissipation due to shear force. So the process is reversible. So reversible adiabatic process means adiabatic process is q equal to 0. Q equals 0. Reversible adiabatic process is termed as what? Isentropic process. Isentropic process means delta S equal to 0 or S equal to constant. So since we have derived the equation A equal to the root of dP by d rho, based on the assumption that S equal to constant, we have to write it as A equal to, we have to change it, dou P by dou rho at constant S. So this is our equation. Okay, the fundamental expression for speed of sound is in any medium, A equal to root of dou P by dou rho with constant entropy. Okay, constant entropy. Students, acoustic velocity in incompressible fluid. So what is incompressible fluid? Incompressible fluid is change in density is 0. So incompressible fluid is nothing but there is no change in density. So dou rho will approximately equal to 0, right? Since A equal to integral, so root of dou p by dou rho at a constant entropy, at constant entropy. If dou rho is equal to 0 means this is 0, denominator is 0, denominator is 0 means a a will approach infinity. The sound of velocity, acoustic velocity in case of incompressible fluid will be infinity. It means if a pressure pulse emitted anywhere in that fluid will be felt anywhere, any other point in that field simultaneously, okay, with no time lag. So if this is our fluid field, I'm producing a pressure pulse here. At the same instant, anywhere in the field you can feel that sounds, because acoustic velocity is having a value of infinity. So at no time it will reach any other point in an incompressible fluid. Why? Because A equal to dou p by dou rho at constant s. So since dou rho is 0, A will be equal to infinity. That's the idea behind the incompressible fluid. Now, what do you mean by K? K is bulk modulus. K, bulk modulus. Have you heard of K? You might have studied in fluid mechanics and solid mechanics too. Bulk modulus is nothing but the modulus of elasticity in case of hydraulic stress. So since if I am having a body, a fluid element, if this is pressure force is acting from everywhere, from all six direction, what will happen? This body will get compressed to a smaller size, right? So if compression means if initial volume was V, it will compress to V minus dV. Okay. So strain can be written as minus dV by V. So stress is nothing but value will be pressure P itself. So bulk modulus Vk can be written as stress by strain dP by minus dV by V. Okay. So Ks at constant entropy, constant entropy K will become Ks. Okay, constant entropy. So students, dV by V can be written as d rho by rho itself, right? Since V equal to m by V, mass by volume equal to rho, right? Wait. It's actually rho is mass by volume equal to rho, right? So if volume is decreasing means density will increase. Volume decrease means density increase. So if volume decrease to minus with V minus dV, density will increase rho plus d rho. So the change the change minus d, the decrease in the right, the strain here is almost equal to d rho by rho. Since this is increase, this is decrease, this is having minus, this is positive. Okay. So K can be written as dP by, instead of minus dV by V, you can write d rho by rho. So if you are having constant at constant entropy, this can be written as at constant entropy here also. Students, what is Ks? Ks is dP by d rho, and I am taking this rho to numerator s. Okay. What is this? There is nothing but a, right? Sorry, a square, right? a square. So ks is nothing but a square rho, right? So a square equal to ks by rho, a equal to root of ks by rho. Okay, so this is another equation for acoustic velocity. So a can be written as root of dou p by dou rho at constant entropy, also equal to modulus of velocity by root of modulus of bulk modulus of velocity by what, by rho. So these are two equations. So students, in case of a perfect guess, we know P specific volume raised to gamma equal to constant for adiabatic process or isentropic process, right? So V is small v is inverse of, sorry, V should be equal to rho, 1 by rho, right? Since small v is mass by volume, small v is volume by mass, specific volume, right? This is nothing but 1 by rho. So you can write PV small raised to P into small v raised to gamma equal to constant is nothing but P 1 by rho whole raised to gamma equal to constant, or P equal to constant into rho raised to gamma. So this is an equation for adiabatic process, right? So I am taking log on, applying natural log on both sides, ln. So what will become? Log P equal to log C plus gamma log P. Okay. So if I am taking differential, so differential of log P will be and differential will be dp by p equal to differential of, this is a log C is constant itself, so this is 0, as gamma dp by p. Sorry, this should be rho, right? Rho, d rho by rho. So if I take dp by p is equal to gamma d rho by rho. So I am taking this d rho to this side. dp by d rho equal to gamma p by rho. This is at constant entropy. That is why we have to, since we have taken this equation, this can be written as at constant entropy. So this equation is valid for perfect gas only. That is why I am telling this is applicable for perfect gas. Okay. Now dp by d rho at constant entropy is gamma p by rho, right? So what is this? This is acoustic velocity square. It's nothing but gamma p by rho. So a is nothing but square root of gamma p by rho. So what is pv? P small v equal to rt, right? Or p equal to rho rt. So P by rho will be equal to RT. So this can be substituted as A equal to root of gamma RT. So A equal to root of gamma RT is another equation for perfect gas. For perfect gas you can use this equation. So in case of perfect gas only you can apply this equation. All other case you have to use the other equation system. Okay. So R is characteristic gas constant. If you are having a universal gas constant, you can universal gas constant R bar by uh, molecular weight of that particular gas into T. So here R is universal gas constant. Okay. So since the variation of gamma between gases is very small, the molecular weight of the gas takes a major part in deciding the velocity of sound through that medium. Okay. So the gases with lower molecular weight have large sound velocities and vice versa. So that is the concept of acoustic velocity or the equation for acoustic velocity in perfect gas. So students, another term I am introducing is Mach number. Mach number. So Mach number at a point in a flow field is defined as ratio ratio of local velocity v of flow at that location to the velocity of sound, velocity of sound a velocity of sound a at the same location, so the ratio velocity of a flow field at a particular location to the velocity of sound in that medium, for that medium in that same location. So Mach number m is v by a. So this is very important. Mach number is a dimensionless number because same this to our velocity only. So Mach number has got no dimension, so it is a dimensionless parameter named after some physicist called Ernst Mach. Okay, so it is a dynamic similarity parameter used in the analysis of compressible flow. So another definition for Mach number is Mach equal to square root of inertia force. So don't worry about this equation. You just understand that it is also defined as square root of inertia force to elastic force of fluid. Elastic force of fluid. So it can be written as integral or square root rho a v square. Inertia force is rho into a into velocity square by elastic force is nothing but bulk modulus of velocity into area of flow, cross-sectional area. So here area and area cancel, rho v square by ks. Okay, so since ks is rho into a square, you can write Mach number equal to rho v square by rho a square. Rho cancel, you get root of v square by a square equal to v by 8. Okay. So don't worry about all these things. You just focus or concentrate on the point that Mach number is defined as ratio of velocity of the fluid field at a particular point to the velocity of sound in that medium at that particular location. So what is the importance of Mach number? It gives Mach gives importance of direct energy and thermal energy in that flow. So the velocity v measures the directed motion of the gas particles, and v square measures the kinetic energy of the directed flow. Okay. So okay, leave all those things. You just try to understand that m is v by a. So rest the remaining portion we will discuss in the next session. So as of now we can stop. Okay, thank you.